Imagine a place in the universe where gravity is so intense, so overwhelming, that it bends the very fabric of reality itself. In this extraordinary environment, even light is forced into a circular orbit, unable to escape the gravitational grip. This is the photon sphere, a ghostly, shimmering shell of light forever trapped by the immense gravity of a black hole. Here, photons, particles of light, race endlessly around the black hole, caught in a delicate dance. If nudged outward, they might escape to the universe. If nudged inward, they spiral into oblivion. The photon sphere sits just outside the event horizon, which is the infamous point of no return. Cross it, and nothing, not even light, can escape. It's a razor-thin boundary where the speed of light and the pull of gravity are perfectly balanced, but only for a fleeting, precarious moment. If you could somehow stand at the photon sphere, you'd witness a mind-bending sight. Light would circle the black hole and return to you, allowing you to see the back of your own head, or even multiple images of yourself all at once. This bizarre phenomenon is a direct result of Einstein's general relativity, which tells us that massive objects like black holes warp space-time itself, curving the paths of everything, including light. Black holes are the ultimate expression of this cosmic warping, creating a gravitational well so deep that nothing can climb out once it falls in. Light, which normally travels in straight lines across the universe, is forced into these extreme looping curves, becoming a prisoner of space-time itself. We can't see black holes directly because they emit no light, but we can observe the dramatic effects of their gravity on the light from nearby stars and gas. The photon sphere acts as a glowing marker, a cosmic signpost that reveals the presence of an otherwise invisible monster lurking at its center. By studying this trapped light, scientists can measure a black hole's mass and spin, probe the nature of gravity, and even test the predictions of Einstein's theories in the most extreme conditions imaginable. The photon sphere is our window into the most extreme physics in the cosmos, a glowing ring that lets us peer into the heart of darkness and glimpse the true power of gravity. How does the photon sphere form? What makes this mysterious region possible, and why is it so unique in the universe? It's a cosmic balancing act between gravity pulling inward and a photon's momentum pushing outward. The black hole's immense gravity tries to draw everything in, while the photon's incredible speed resists, creating a delicate standoff. The photon sphere is the precise location where these forces reach a fragile equilibrium. Here, light doesn't fall in or escape, but instead orbits the black hole in a perfect, razor-thin path. Imagine a photon as the fastest thing in the universe, racing around the black hole at the only possible stable orbit for light. It's a breathtaking cosmic speedway, where light circles at unimaginable velocities. But this balance is unstable, like balancing a pencil on its tip. Even the tiniest nudge can break the spell. The slightest disturbance sends the photon either plunging into the black hole or escaping into space. There's no room for error in this cosmic dance. The photon sphere isn't filled with ancient, trapped light. It's a dynamic region, constantly replenished by new photons passing at just the right angle. Each photon's journey is brief, and the population is always changing. Light from distant stars can be temporarily captured here before being flung away. The photon sphere acts as a cosmic lens, bending and redirecting light from across the universe. This constant flow makes the photon sphere a faint but visible feature. It glows subtly, marking the border between the known and the unknowable. It's not a static shell, but a river of light, always in motion at the edge of darkness. The photon sphere is alive with movement, never the same from one moment to the next. The photon sphere's instability means it's a fleeting, ever-changing boundary. Its shape and brightness shift constantly, shaped by the chaos around the black hole. Only photons on a perfect path can linger, and even then, not for long. Most are quickly lost, making the photon sphere a place of constant renewal. This delicate dance is what makes the photon sphere so fascinating and so difficult to observe. It's a testament to the strange and beautiful physics that govern our universe. The Schwarzschild radius defines a black hole's event horizon, marking the boundary beyond which nothing, not even light, can escape the black hole's immense gravity. But just outside this invisible boundary lies the photon sphere, a mysterious region where gravity is so strong that light itself can orbit the black hole in a perfect circle. The event horizon's radius is calculated as Rs 2GMC2. where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. This elegant formula links the mass of the black hole directly to the size of its event horizon, making it a cornerstone of black hole physics. For a non-rotating black hole, the photon sphere's radius is exactly 1.5 times the Schwarzschild radius, a simple but profound relationship. This ratio is a remarkable prediction of Einstein's general relativity, showing how gravity bends the very fabric of space and light. If we can observe the photon sphere, we gain a direct window into the event horizon size and by extension the black hole's mass, unlocking secrets hidden in the darkness. For spinning black holes, known as Kerr black holes, the situation becomes even more fascinating and complex. The black hole's spin distorts the photon sphere, creating different possible orbits for photons depending on whether they move with or against the spin. Prograde orbits, where photons move in the direction of the spin, are pulled closer to the event horizon, while retrograde orbits moving against the spin are pushed farther out, creating a lopsided photon sphere. The shape and distortion of the photon sphere reveal not just the mass, but also the spin and orientation of the black hole itself. These relationships give astronomers powerful tools to probe black holes, allowing them to test the limits of physics in the most extreme environments in the universe. The photon sphere's size and shape are cosmic signatures, unique fingerprints that reveal the hidden properties of black holes and help us understand the universe's most mysterious objects. The photon sphere is responsible for the iconic black hole shadow. This shadow isn't the event horizon but a dark region created by extreme gravitational lensing near the photon sphere. Light passing close to the photon sphere is bent so much that it defines the shadow's edge. The shadow appears larger than the event horizon, magnified by the bending of light. The bright ring we see is light from the accretion disk, lensed into a circle. The shadow's size is about 2.6 times the photon sphere's radius. By measuring this shadow, astronomers can calculate the black hole's mass with remarkable precision. The shadow is our most direct visual evidence of the photon sphere's existence. The photon sphere is the ultimate gravitational lens, bending light into a cosmic hall of mirrors. Light passing near the photon sphere can loop around the black hole multiple times before escaping. This creates a series of nested photon rings, each a lensed image of the entire sky. The brightest ring is from light making a single half-orbit. Fainter rings come from light looping around more times. Each ring encodes information about the black hole's mass, spin, and the geometry of space-time. Current telescopes can only resolve the main ring, but future instruments aim to capture these finer structures. Observing these sub-rings would be a powerful test of general relativity. The photon sphere's lensing effect turns black holes into cosmic projectors, revealing the universe in astonishing ways. Every photon ring is a message from the edge of the abyss. Decoding them could unlock new secrets about gravity and the fabric of the cosmos. Black holes and their photon spheres are the ultimate testing grounds for Einstein's theory of general relativity. The photon sphere's size and the shadow it casts are precise predictions of Einstein's equations. When the Event Horizon Telescope imaged the black hole in M87, the shadow's size matched general relativity's predictions exactly. Any deviation would hint at new physics beyond Einstein. Alternative theories predict different shadow sizes or shapes. By measuring black hole shadows ever more precisely, we test the very foundations of gravity. The photon sphere also lets us probe magnetic fields and plasma near the event horizon. Every photon escaping this region carries clues about the nature of spacetime. The photon sphere is where theory meets observation in the most extreme environment known. To understand the photon sphere, we must see the universe as Einstein did, a four-dimensional fabric called spacetime. Gravity is the curvature of this fabric, not a force. A black hole creates a bottomless pit in spacetime, and the photon sphere is a critical point on its slope. Here, light follows a circular path called a null geodesic, the straightest possible path in curved spacetime. For non-rotating black holes, the photon sphere is a perfect sphere, allowing precise calculations. Real black holes often spin, distorting the photon sphere and breaking its symmetry. Photons orbiting with the spin get closer to the event horizon than those going against it. This leads to complex shadow shapes, revealing details about the black hole's spin and geometry. By analyzing these shapes, we map the warped space-time around black holes. The photon sphere is a geometric fingerprint of the universe's most extreme objects. For years, photon spheres and black hole shadows were theoretical, until the Event Horizon Telescope changed everything. In 2019, the EHT captured the first image of a black hole shadow in galaxy M87, revealing a glowing ring around a dark void. The shadow's size matched general relativity's predictions for a black hole of M87's mass. In 2022, the EHT imaged Sagittarius A, the black hole at our galaxy's center, despite its rapid variability. Both images showed the photon sphere's influence, turning theory into observation. The ring's brightness varies due to Doppler beaming, revealing the black hole's spin direction. Polarization studies are mapping the magnetic fields shaping the plasma around black holes. These observations have made photon spheres a tangible subject of astronomical study. The first black hole images are just the beginning. Next-generation telescopes aim to resolve the finer nested photon rings predicted by theory. Measuring these rings would provide the most stringent test of general relativity yet. Any deviation could point to new physics, perhaps even quantum gravity. We also seek to understand how photon spheres influence accretion disks, magnetic fields, and jets. The quest to study photon spheres pushes the limits of technology and human curiosity. These luminous boundaries promise to reveal even deeper secrets about space, time, and gravity.